Okay, hello. So we're really happy there is such an interest in multi-cluster batch schedulers. So my name is Dejan Pejchev. I'm an open source software engineer with the G Research open source software team. So we'd like to welcome you to our talk, Multi-Cluster Wars, the Scheduler Awakens. So with my colleague, we'll walk you through batch scheduling and do a deep dive of how various batch schedulers approach the concept of multi-cluster. So Pinky.
Hi, my name is Priyanka Ravi. I also go by Pinky, and I am a tech advocate at G Research. Before we dive into schedulers, I want to set the stage with the why. Why batch scheduling is important, where single clusters start to fall apart, and why multi-cluster scheduling becomes necessary. And once we've got that foundation, I'll hand things over to Dan to walk us through the schedulers themselves and different approaches the ecosystem offers. Batch scheduling is all about coordinating workloads that start, run, and complete. Things like training, jobs, simulations, pipelines, analytics, or research webhooks. Research workloads. We all either had to deal with or know people who were stuck in that massive line yesterday to get into this conference center. It's actually the perfect metaphor for how scheduling goes wrong when the system isn't designed for scale. Every batch scheduler, regardless of how sophisticated it is, uses the same core primitives. So the first is queuing and prioritization. First in, first out is cute, but not for production or conference lines. We need a coordinator at the door, critical jobs up front, experiments later. Yesterday's security line didn't do that. Speakers, staff, and attendees were all in the same queue. In a cluster, that's like letting latency-sensitive workloads wait behind test jobs. The goal is to ship the important stuff first without letting hardware slide. So the second is bin packing. Think Tetris with CPUs, GPUs, and memory. In that security line, it's like leaving the other entrances empty, which they were, because no one's directing traffic. Good packing fills every lane and every node efficiently. When we waste little pockets of compute, we're basically leaving money scattered across the cluster. Gang scheduling. Some workloads are a band, not soloists. Everything must start together or it sounds awful. We launch the whole gang or nothing, so MPI and training jobs don't half start and block everything else. Fair share prevents hogs. It's the equivalent of not letting one badge printing station take all the attendees while the others stay idle. Policies steer heavy users down and light users up over time, so everyone gets predictable access, even during rush hour. Preemption and backfilling, these are our two moves to keep the cluster responsive. Preemption, bump low-value work so urgent jobs start now, kind of like pulling a late-running keynote speaker to the front of the line. Backfilling, while big jobs wait for enough nodes, slip in short jobs that fill the gaps, like letting a few attendees with no bags breeze through a side lane. Utilization stays high without breaking promises. And lastly, we have placement and locality. Move compute to data, not the other way around. Latency, egress, and compliance, all thank you. Yesterday, some entrances had 0 lines, like I said, but no one knew. Same idea in clusters. We need visibility into where the capacity actually is and the freedom to route workloads to those emptier entrances. Put together, smart queues, tight packing, atomic starts, fair access, tactical preemption, and smart placement. That's how you turn a noisy cluster into a predictable, high-throughput compute factory. Or, a conference line that actually moves, like it did today. Why not a single cluster? Let's talk about the drawbacks of a single cluster setup. So the first is performance bottlenecks. Past a certain size, adding nodes feels like pouring water into a full cup. Most of it spills as overhead. Controllers, leader elections, reconciliation traffic start eating your gains. You buy more compute, but throughput plateaus and tail latencies creep up. In our analogy, that's like opening more security lanes in the same congested hallway. You're not fixing the choke point, you're just moving it. Control plane pressure. The API server and etcd don't just run your apps, they carry everyone's feelings about your apps. A chatty operator or CRD explosion can turn into a thundering herd of list or watch events. Suddenly the scheduler's playing whack-a-pod while API P99 climbs. API P99 means the 99th percentile latency for your API. Imagine if the overhead security staff were scanning every badge twice because too many people were requesting their attention. Single point of failure and maintenance pains. One cluster means one big blast radius. Routine work such as node drains, CNI upgrades, control plane patches, they become a platform-wide nail biter. So it would be like having only one entrance open. If it closes, the whole crowd stops. Even planned maintenance becomes a stress test. And lastly, we have data gravity, compliance and latency. Data wants to stay where it lives. Users here, training sets there, regulators somewhere else. A single cluster forces you to choose between dragging data across borders, hello compliance, or dragging users to the data, goodbye latency. That's like forcing every attendee to walk through the same doorway, even if the keynote or their session is on the opposite side of the building. All right, why multi-cluster? There are several benefits of using multi-cluster scheduling, the first being high availability and disaster recovery. Instead of one giant basket for all your eggs, we stitch together clusters in different regions and different data centers. If one goes sideways, such as a power blip, network flap, or maintenance oops, or maybe you're on US East 1, the scheduler steers new work to healthy clusters. Failures become detours, not roadblocks. Think of it as having multiple entrances. If one gets clogged, attendants redirect people to another open lane. And then we have data locality, which is compliance and latency. With multiple clusters, we can move compute to where the data lives, or place data near the compute without breaking laws or user patience. Keep EU data in the EU, keep training sets near GPUs, and let the scheduler respect those boundaries. It's like having separate entrances for badge pickup and fast-track attendees. Same attendant, same event, better flow. Workload isolation and multi-tenancy. Different teams, different noise levels. Multi-cluster gives each tenant a real-life blast radius boundary, and noisy neighbors stay in their lane. If one line's full of people with luggage and metal water bottles, the no-bag line still moves. If one team melts down their cluster, everyone else keeps going. Scalability. Escape the big cluster ceiling. When a single cluster hits control plane pain, such as etcd churn, API P99 spikes, scheduler backlog, we scale out, not up. More clusters means smaller state shards, less fragmentation, and no wrestling with those 5K node, 150K pod ceilings. It's like opening every entrance around the building and finally distributing the crowd evenly. So, if yesterday's long security line taught us anything, it's that even well-intentioned single queues can hit scaling limits. Multi-cluster scheduling is how we open all the doors, keeping throughput high, latency low, and everyone moving. With that foundation, I'll hand it over to Dejan, who will walk us through the schedulers themselves and how each one tackles these exact challenges in different ways.
Thank you, Pinky. So, for the next part of the presentation, now let's do a deep dive and analyze a couple of schedulers and their approaches to multi-cluster. So, the first one, I'm sure you're familiar with, is Volcano. Volcano is a popular scheduler, and Volcano Global is the multi-cluster version of Volcano. And it actually took quite an interesting approach. So it uses Karmada for the multi-cluster control plane, and lets Volcano scheduler handle batch scheduling inside each cluster. Quick note about Karmada. So Karmada is a CNCF project that gives you a multi-cluster control plane. You interact with management cluster where Karmada runs, and Karmada propagates workloads and policies to the right worker clusters. Karmada is fully compatible with existing Kubernetes toolchain and adds support for multi-cluster basics like auto-scaling, failover, load balancing, plus placement controls like cluster affinity, cluster splitting, cluster rebalancing. And by the way, when I say placement, I mean the decision of which cluster or cluster should run a given workload. Volcano Global consists of two components, the webhook component and the controller. So the webhook, when a new placement shows up, it taps the brakes just for a moment, so we can look across all clusters instead of blasting it to the first one that's free. Then the controller. While it's paused, the controller decides where it should run, taking priorities and fairness into account, then leaves the hold so Karmada fans it out to the chosen clusters. Here's a little diagram of, well, maybe not so little, of how Karmada looks like. I'll just quickly go through some components for better understanding of what's to follow. So we have the Karmada API server. It's the front end of the control plane. It exposes the Karmada API alongside the Kubernetes API. We have the Karmada controller manager, which is Karmada's custom controllers which manage Karmada CRDs. Karmada has a scheduler, which schedules workloads to worker clusters. It evaluates constraints, available resources. It ranks valid clusters, and then it binds the resources to the most suitable cluster. There is a webhook component, which is admission webhooks, a mutating and a validating one. With the mutating one, you could set defaults. With the validating one, you can enforce policies. You can reject various workloads. etcd is the data store of Karmada, similar to how Kubernetes uses it. You also have a scheduler estimator, which analyzes worker clusters and provides the scheduler with more accurate cluster resource availability. And there is a descheduler component, which periodically detects state changes in worker clusters and can trigger reschedules to other clusters. So TLDR would be, there is a kube-native API surface at the top, an admission and scheduling in the middle, and concrete resources realized in worker clusters. And all of them kept synchronized by Karmada's controllers. Now here's a diagram of how Volcano Global leverages Karmada and achieves multi-cluster scheduling. So a user submits, let's say, a Volcano job to Karmada. Karmada's API turns that into a placement request. Then the Volcano Global webhook catches that new request. It pauses scheduling. And this brief hold gives us a moment to evaluate all clusters and pick the best one or best ones. The Volcano Global controller watches paused requests, looks up the related queue, then it applies queue priority, it applies job priority, and any queue capacity, fairness rules, all of those scheduling concepts, and then, if admitted, resumes the request. Once resumed, Karmada performs the actual multi-cluster placement to the selected cluster or clusters, and then on each chosen cluster, the Volcano scheduler does the node-level scheduling and runs the workload. So here's an example how we can interact with the Karmada management cluster. We could get clusters, so we could see which worker clusters are connected to Karmada. And then on the right side, we can see how we can interact, how we can submit a Volcano job to the management cluster, and then Karmada will eventually fan it out to a worker cluster and schedule the pods to be executed there. Next one, which is a project which is dear to me, is Q. So Q is a Kubernetes native batch scheduler, and Q is as native as it gets. The beauty of Q is that it only relies on vanilla Kubernetes without any external dependencies. So Q and multi-Q you just install, you don't need anything else. So users submit various workloads, and Q brings the batch scheduling concepts they need, like the ones we mentioned, queues, quotas, fair share, gang scheduling, preemption, and various others. And multi-Q takes the same model and applies it across multiple clusters. So with multi-Q, you have one management cluster wired to many worker clusters. And as a user, you interact with the management cluster by submitting workloads, you watch their statuses, you do all of that with the management cluster. And under the hood, multi-Q clones your workload to a chosen worker cluster. It mirrors it between the management and worker cluster and syncs the status back. That way, all of your tooling, which was pre-wired with the management cluster, works exactly as before, even though the actual execution of the workloads is happening in a completely different cluster. Now, how Q managed to achieve multi-cluster? The clever bit in that is for multi-Q's support for multi-cluster lies in job managed by Kubernetes enhancement proposal. So that's a change in Kubernetes, which recently got promoted to stable. So that proposal introduces a field in the job definition called managed by. And when that field is set, it marks a job object as managed by an external controller. thus effectively disabling the local job controller in the cluster. So now what happens? On the management cluster, multi-queue creates the job object. It sets the managed by field, which disables the local job controller for that object, so we avoid double scheduling. And then multi-queue submits it to some worker cluster it finds most appropriate based on our scheduling requirements. It mirrors the objects and keeps their statuses in sync between the management and the worker cluster. Now, to introduce a couple of queue concepts. So there is a local queue, which is like a Teams inbox. So local queue is a namespace resource that groups closely related workloads belonging to a single tenant. Next level is a cluster queue. So cluster queue is a cluster scoped resource that governs a pool of resources. It defines usage limits, it defines fair sharing rules, it can also define quotas for multiple flavors. For various compute resources like CPU, like memory, like GPU. It can also define admission checks, and admission checks are also a concept which I'm amazed by how Q implemented it. It's a concept where you can have external signals which control when a workflow can be admitted. Then we have a resource flavor. That's an object that defines available compute resource in a cluster, and it enables fine-grained resource management by associating workflows with specific node types. So now we don't just say, give me one GPU. Instead, we say, for example, we define a resource flavor which can say, give me one NVIDIA A100 in US East 1A on a spot instance. Also, what I mentioned, admission checks. So admission checks are a mechanism that allow Q to consider additional criteria before admitting a workload. So after quota is reserved, Q or multi-Q runs all configured admission checks in parallel. Only if all of the admission checks report a ready status, only then the workload gets admitted and it resumes execution. So to summarize, a team submits to a local queue, Q creates a workload, sends it to a cluster queue, it reserves a resource flavor quota, then when all admission checks become ready, job is admitted and resumed. So now back to multi-queue. First, we set up the worker clusters. So here's an example of a very basic setup, how it might look. On each worker cluster, first we set up a standalone queue cluster, and we need three things to mirror from the management cluster. Most basic example would be to configure everywhere a local queue, a cluster queue, and a resource flavor. And we need to make sure the names match. So how we name them in the management cluster is the same how we should name them in the worker clusters. Then on the management cluster side, we define the same three resources, which are shown on the right, with one exception. So we add an admission check to the cluster queue, which is marked with a white box. And that is what makes all the difference and transforms queue into multi-queue. So we define an admission check. The admission check definition is shown on the left, which targets the multi-queue controller. We parameterize it by providing the kube configs of our worker clusters. And when it becomes active, this cluster queue is eligible for multi-cluster placement. So the flow goes like, you submit to a local queue, cluster queue reserves by flavor, then multi-queue admission check runs, and picks a worker cluster based on scheduling requirements and available capacity. Multi-queue clones the job to the worker cluster and syncs the workload status back. If for any reason the admission check isn't active or a worker cluster connection is down, the workload won't be admitted and it will be in suspended state. So here's an example how we can interact with the management cluster. You can see that we submit a job to the management cluster, we get the job status, we can describe the job from the management cluster, and multi-queue under the hood will schedule it on the most appropriate worker cluster, and in real time it will mirror the status back, so we can interact only with the management cluster. Now, last but not least, multi-cluster batch scheduler, which I'm personally attached to. So Armada, a pioneer in multi-cluster batch scheduling. It was created in 2019. It became a CNCF sandbox project in 2022. So the architecture consists of a control plane, the control plane having an API server, a multi-cluster aware scheduler, and a UI component, and a cluster-side executor that runs the workloads in the worker clusters. So it follows a robust async and event-driven architecture. It uses battle-tested tools like Apache Pulsar, Postgres, and Redis in the heart of it. So from a usability angle, Armada offers a CLI, APIs, plus client libraries, having client libraries written in Go, in Java, in Scala, .NET, Python, and integrations with systems like it can integrate with Airflow, you can run Spark workflows on Armada, you can run OpenMPI workflows on Armada. And Armada is designed for a special use case. Armada is designed for high throughput and large-scale scheduling. So think of tens of millions of jobs per day and compute farms which are larger than, let's say, 50,000 nodes broken down into, let's say, dozens of Kubernetes clusters. Also, an interesting thing about the design is even though Armada is used to schedule workloads in Kubernetes, the design of the control plane makes it possible to implement new cluster-side components which satisfy the scheduling interface and, in theory, could integrate with other batch scheduling platforms like, for example, Slurm. A bit on the concepts of Armada. So queues control how work gets organized, and queues also enforce fairness. Every job lives in exactly one queue, and fairness is computed over time per queue. When a job is picked, it moves into a lease state. The scheduler decides where it should run. The executor then pulls that decision, creates the workload in the appropriate Kubernetes cluster, and reports back. If a lease can't be honored in time, Armada can reoffer that work elsewhere to a different cluster. Preemption is also a big concept in Armada. It comes in two flavors. One is urgency-based preemption, which is like the traditional preemption. Higher priority jobs can preempt lower priority ones. The other one, which is more interesting, is preemption to fair share. Preemption to fair share is if at some moment you don't have that many active queues, queues can go over their fair share. And when other queues again become active, meaning users start submitting to them, preemption to fair share will kick in, and it will start preempting jobs of the queues who breach their fair share limit and restore balance over time. Also, to protect the control plane, Armada enforces rate limits and throttling on submissions and scheduling. It's very useful during bursts, so neither API nor schedulers get overwhelmed. Also, on top of that, Armada supports various auth options and a fine-grained RB configuration, so you can implement various roles in Armada. So here's a diagram of the Armada control plane and the executors. So users talk to the Armada control plane. New work lands in the control plane first. The Armada scheduler then decides which cluster should run it and can preempt lower value work when needed. Like I said, under the hood, it's fully async and event-driven. Apache Pulsar is the log of truth. Postgres stores jobs in history. Redis holds fast in-memory states, so scheduling stays responsive at high volume. Downstream, executor, the cluster-side component, runs in each Kubernetes cluster. They're plug and play. They register with the control plane. They list jobs. They create the Kubernetes objects and report progress back. So given this image, the approach which Armada uses is inverse of the one which multi-queue use. In multi-queue, you configure the worker cluster in the management cluster, and here Armada follows a plug and play, where executors connect to the Armada control plane. Here's an example how user can interact using the CLI. So it's easy to drive from the CLI. We create a queue, then we submit a job. The YAML on the right is a pod-like spec with a few Armada extras, queue, job set ID for grouping retries, and scheduling hints like priority class name, tolerations. So you keep the Kubernetes feel, but get batch-friendly knobs out of the box. Also, Armada comes with a nice UI component called Lookout. And from here, you can browse jobs and job sets, filter by queue, job set, state, ID. You can drill into jobs details. You can also examine scheduling result, look at logs. You can also interact from here, like from the Lookout, you could cancel jobs, you can reprioritize them, so you don't need to hop constantly to the CLI or to the API. And with that, Pinky, would you be kind enough to
close us out.
give some closing remarks.
Yeah. So if you think back to that line outside the conference center yesterday morning, all those people funneled into one checkpoint, that's our single cluster galaxy. Batch scheduling brings a bit of order, but multi-cluster scheduling is where balance truly returns. It's when we open all doors, route intelligently, and finally restore harmony between compute and data. In other words, the force is strong with multi-cluster. Thank you all, and may your pods always be scheduled where they belong. Also, I just want to say before we take questions, G Research is hosting a happy hour, and we are hiring. But also, if you want to just come hang out with us, network, please feel free to scan this QR code and come join us. This slide is a joke, mostly. You can ask us questions now. We'll take them.
There we go. I had a question for multi-queue. You were talking about the admission check, and prior to that, it was reserving resources. What happens if that admission check doesn't come back okay? And if you have like a poorly designed admission check, could that lead to a ton of resources getting reserved over and over, but never actually getting scheduled?
So the job would definitely get in a suspended state. I think the resources shouldn't be reserved at that point. But yeah, it would be stuck in a suspended state.
Okay, yeah. I thought you said that the resources had already got reserved. That's where my concern was, but if that's not the case, then that should be fine. Thank you.
Thank you.
Hello. Good talk. Thank you.
Thank you.
Do any of the solutions you described solve the problem of running one workload across multiple clusters? Like, say I need more pods than a single cluster can run. Can it run on two clusters at once?
Armada definitely supports that, so yes.
So with Armada?
I mean, I can vouch for Armada.
Excuse me?
I mean, I can vouch for Armada.
Okay. Cool.
He's
Thanks.
saying he knows for sure that one, but we're not sure about the other two.
Thanks.
Okay, so if there aren't any further questions, I guess we can wrap up. Thank you for taking such an interest in this. Hope you liked our talk.
Thank you.
Thank you for attending.